Welcome back, everybody. Today our lecture is going to be an entire digital lecture because the lecture hall is occupied due to other activities. The plan for this week is to repeat some of the expressions which we discussed last week, especially linked with the gradient methods. And we are going to look at some of the shortcomings and how to improve upon the shortcomings. So today is going to be a lecture where we dive a little bit more into the technicalities of the optimization itself, and in particular in the calculation of gradients, and see how we can use this to get the best possible estimates for the unknown parameters of the model. The examples which we are going to look at, they are examples which link up both with logistic regression and the standard linear regression, and we saw that last week for some of the examples for linear regression, that we actually ended up getting the same expression when we operated on the full data set which entered the calculation of the gradient. On Friday, we're going to continue with this discussion, and we're also going to look at an algorithm which is called automatic differentiation, which is one of really, what I'd say, one of the really great algorithms. And this is normally translated into a software like auto differentiation or autograd, as it's called in Python, and lately into what is called JAX, which we will discuss a little bit about tomorrow. And the focus will also be on stochastic gradient descent and different ways of finding the optimal learning rate. So many of the technicalities which are going to see both today and tomorrow, they are going to deal with ways to tune the learning rate. So there are some pretty good notes in the textbook by Goodfellow et al., in particular in section 4.3 and 4.5. And feel free also to take a look at chapter 8. Now, chapter 8 is a chapter which we will come back to again and again when it comes to neural networks. So chapter 8, and in addition chapter 7, which is much more linked to the discussion neural networks, is something we will keep picking up next week and the week thereafter when we begin with neural networks. And if you want to look at the hands-on implementations of some of these methods, the text by Geron in chapter 4 is actually a pretty good read. Now, what I wanted to do now is actually to bring back the expressions which we looked at last week. So let's just dive into the whiteboard. And since we now today are having an entirely digital lecture, feel free to use the chat function and ask questions in the chat. The lectures are going to be recorded and posted online as before. So let me just stop sharing here and then switch to the whiteboard and bring up some of the equations which we looked at last week. So one of the things which we did last week was actually to look at a Tailor expansion of the cost function in terms of the parameters. So we had a Tailor expansion. I just wanted to bring up these expressions here so that we are on the same level. So we had a Tailor expansion of the cost function, C of beta, where beta is now the unknown parameter or the unknown parameters, since we are going to have many beta values. And we made an expansion around the optimal parameter beta. So what we did was to assume that this beta which we have is actually the optimal parameter which we get after we have optimized the problem or minimized the cost function. So when we then performed a Tailor expansion, we did a Tailor expansion around beta minus, so I'm just going to use beta instead of beta hat, minus the result from the previous iteration. So the cost function then expanded around this beta n value is given by a constant term, beta of n here. And then we had plus, and we got a term which was given by the gradient. And this gradient is calculated for beta of n. So G is the gradient of the cost function. So let me quickly remind you of that. And I'm not putting vector signs on top of them but it should be understood from the context here that these are vectors and matrices. So G is now given as the gradient with respect to beta of C of beta. So we are calculating the gradient at a given point. So this is, since the cost function is a scalar, the mean squared error is a scalar, just a number, then we have to multiply this with beta minus beta of n. And remember again that beta is a vector, plus, and then we have the second order term. And in this case, we had a beta minus beta of n transpose. And the second derivative, as we discussed in the previous week, is given by this Hessian matrix. So this is the second derivative. And this is also calculated at the value beta of n. And we have to multiply this with beta minus beta of n. And then we have all the higher order terms. Now, typically what we would do is to truncate this expression at the level of the second order term. So that means that the cost function now is approximated with the constant term, which we have here. It's approximated with the gradient multiplied with the beta minus beta n term. And then we have the term with the second derivative, which is this term here. Now, this is obviously a little bit different from what you would have if you had scalar quantities only. So the betas are vectors, H is a matrix, the gradient is a vector, and C beta of n is just a scalar. So when we take the transpose of G multiplied with beta minus beta of n, this becomes also scalar because just the inner product between the vector for the gradients and the vector for the parameters beta. So you could rewrite this. So one of the things we did last time was actually to rewrite this in terms of a new vector, which we simply defined as a vector B, which was given by beta minus beta of n. And then we could rewrite everything in terms of C of beta. This is given by still the term, the constant term. And then we would have the gradient. And now I'm going to skip the dependence of the gradient on beta n. So I'm just going to write it in a more compact way. So we have G transpose times vector B plus 1/2 of the vector B transpose, and then multiply with Hessian matrix times the vector B. And now we should put an approximation sign here to indicate that we actually truncate this at a specific level here. And then we could then find the iterative expression based on this expression, what we found then, and this is what we derived last week. Then we found that the optimal parameter beta is given by a beta of n, and then we had minus, we have the inverse of the Hessian matrix multiplied with G, and this is now again a function of beta of n, and the same applies to the Hessian matrix. In general, the iterative scheme which we end up with when we have started with a Tailor expansion of the cost function around the final optimal parameter beta for the estimator, then we end up with this specific truncation at the level of the second order term, the second derivative term. Then we have an iterative expression for the unknown parameters beta, which goes like this. Instead of writing our beta hat, we have beta n plus 1, which is simply given by a beta of n minus, and then we have the Hessian matrix, which is also evaluated at this point beta of n, multiplied with a vector G, which is a gradient, evaluated at this point beta of n. Now, this is the kind of iterative scheme we get in case we cannot solve equations analytically. So to summarize a little bit, if we are dealing with the ordinary linear regression, which is a topic for project number 1, then we have an analytical expression for the parameters beta. This is going to be very helpful for us in project number 2 when we are going to write our own gradient descent algorithm. Now, as you see here, this matrix H can be pretty large, and this is something which we would like to avoid to calculate. And the standard recipe is now to compute or replace h with a parameter gamma, which can depend on the iteration which we are at, and multiplied with g of beta of n. And this parameter gamma is a new parameter in machine learning, and it's normally called the learning rate. And this is a parameter. Now, what you see here is that you can actually approximate this gamma in different ways. One of the ways which we looked at last week was simply to put gamma equal to a constant. So that's fully possible. If you put gamma to a constant, the standard recipe is to try to tune this gamma by selecting several values for gamma and find the one which gives you the best mean squared error. This is a typical approach which we are going to encounter again and again. However, we can also find ways to iteratively update this value gamma. So that means that we have a kind of a schedule or an adaptive way of finding the parameter gamma. But the whole problem when we are looking at these types of optimization problems is that, one, we don't want to calculate the inverse of a huge matrix. So if we have many features, the matrix H, the Hessian matrix, which is the second derivative of the cost function, can be a huge matrix to be inverted. You would have to do this at every step in the iteration. So the iteration could contain n equal to 100, or you may even need 1,000 steps to reach the kind of convergence which you are requiring. So typically these recipes, they would stop when you have reached some kind of convergence criterion, where you could typically take the absolute value of the difference between the new iteration and the previous one. And this is normally smaller than some parameter epsilon, which can typically be, let's say, 10 to the minus 8, 10 to the minus 10, or some parameters which you define. So most of machine learning is actually about how do we run this optimization problem in the most effective and most reliable way. Now, if you look at the equation which we have here, we can actually rewrite this in terms of a more general type of problem. So let's look at that and look at some examples in order to try to gain some kind of insight about the type of problems which we have. This will also allow us to bring in other methods. So there are methods which allow us to calculate this parameter gamma here with quite some precision. And then there are other ways which are pretty ad hoc, and other ways which allow for kind of an adaptive improvement of the parameter gamma. And this is basically what this talk or this lecture today is going to be about. So how to find the best and possible value for gamma in the optimization process. Now, if you now look back at this term which you have here, this is nothing but us, if we rewrite this term, so this C of beta is something which I'm now going to replace with a function f of x. And this function can be rewritten in terms of something which looks like the Hessian matrix times the parameter beta. So we can think of a vector x multiplied with a matrix A, multiplied with a vector x minus x transpose times a vector B. Now, if you look back at the expression which we had when we truncated the Tailor expansion around the optimal value for beta, so if you look at this expression here, this is in its vector form, it's actually pretty similar to this. So except that here we have a constant. Now this constant is irrelevant when we are going to take the derivatives. So that means that if we take the derivative of that matrix, and this goes back to one of the exercises we had in the very beginning of the semester. So what we want now is to take the derivative with respect to this vector x. So hopefully you also see that the vector x is a vector and not a scalar. And that follows from the expression here because we have x transposed. So we want to optimize this problem. And that is the same as A times X minus B equal to 0. Now, this translates into a standard linear algebra problem, which we often solve by things like Gaussian elimination. So we have a linear algebra problem, and that is given by A times X equal to B. And many of you have seen this type of problems before. So this is something which we now can relate directly to the kind of approach which we've been doing now. So let's, before we move on, let's now look at one of the standard ways by which we can solve this type of equations. So there is actually a method which allows us to solve this type of problem without having to define a learning rate. So let's take a look at a method which is called the steepest descent. This is not the same as the gradient descent. So although people tend to mix these methods, but let's take a look at the steepest descent, which is a kind of introduction to a set of methods for finding the solution to such an optimization problem, d of x dx equal to 0. And the more refined method is something which is called the conjugate gradient method. Now, these methods, however, are all going to rely on us being able to invert a matrix or calculate a matrix times a vector. So even though they allow us to find a value for this gamma parameter, the learning rate, they become impractical ones when we are getting to larger dimensionalities. But let's go through this method, because in case we have few parameters, the steepest descent is actually one of the simplest way we can implement the optimization problem. So the steepest descent is pretty straightforward to derive, and let's take a look at it. So what we would define then is first a residual, which is actually the error we are making. We call this just the residual error. And the residual error is simply given by the difference with B minus X. And when, obviously, when this residual error is equal to 0, then we have the solution. Now, one thing we can do then, and this is the standard way by which we solve this type of equations, this is to assume a guess for x in the beginning. So there are some questions. So this is a good question. This is actually the symbol, the residual error. This is actually my attempt at writing the letter R. So this is actually my poor attempt at making this one the lowercase letter R. I hope you can forgive me for my handwriting here. Okay, so the typical way is to start with a guess. A guess for x0. So we try then and replace x with an x0, and that defines the residual R0, which is equal to b minus a times x0. And you will notice in many occasions that actually x0 can even be approximated with just 0. So you could even set x0 equal to 0. Okay? Now, the kind of recipe we are going to get then after some iterations, so after k plus 1 iterations, what we are going to have then is an R of k plus 1, which is equal to a b minus a times an x of k plus 1. Okay, so that means that if I now look at my approximation for x, we're also going to assume now that x is actually related to this R of k plus 1. So it means that when we have x at an iteration k plus 1, this depends on the previous value of x plus some parameter alpha, which we haven't specified, alpha of k, multiplied with this residual r of k. So this is a model which we are making now. We make an assumption that we can actually find a parameter alpha k, which uses this residual and improves the value of x at iteration k plus 1. Now, if I then plug this back again, what you can see now, if I go back to the expression here, I can obviously plug in the value of x plus k in here. So that means that in general, what we would have then is that r of k plus 1 is equal to b minus a of x of k plus alpha of r of k. So I'm just inserting the values for x, and we would then rewrite this as a b minus a of x of k minus, and then I have this parameter alpha k of a times r of k. Now, one thing which we are going also to assume is that this vector r of k plus 1 is actually, this is an assumption which is made in addition, is that r of k of rk is equal to 0. So this forms an orthogonal basis set. This means that if I now multiply from both sides with r of k, with r of k transposed from both sides, what we are going to get then is that we have 0, and that's going to be equal to r of k, and then we have the multiplication with the value of beta. So remember now that if you look at this one, this term here, this is actually r of k. This is a definition of r of k. So we would have rk transpose multiplied with rk minus alpha k of rk transpose multiplied with the matrix A and multiplied with r of k. And that gives us an expression for alpha of k, which is given by rk transpose times rk and divided by rk transpose multiplied with the matrix multiplied with r of k. So what you have now, when we go back to the expressions for x of k, so if you look at that one in particular, so what we had is that x of k plus 1 is equal to x of k plus this alpha of k multiplied with r of k. What we can do now, when we make the comparison between what we had before, and if you look at the expressions which we started with, so we started with a d of f of x, of d of x, which is actually equal to a of x minus b, which is obviously the same as minus b minus a of x, a multiplied with x, which is the same as r of k. So what we have then is that the gradient of that function df of x, so that means that d of x of f of x is something which we're going to label as the gradient g of x. We see now that this term here is nothing, this r of k is nothing but the gradient of g of x, or of f of x. So that means that what I can do now is simply to replace r of k with a gradient. So I have x of k plus 1 is equal to x of k in the previous iteration minus alpha of k multiplied with g of x. So here we have an explicit recipe for finding this one. So alpha of k is actually r of k transpose times r of k divided by r of k transpose times a times r of k, which again is the same as the gradient transpose times the gradient at the step k divided by the gradient at the step k multiplied with a and multiplied with the gradient at the step k. So in this particular case, you see that we can actually calculate this so-called learning rate, alpha k, if we know the gradient. And the matrix A is also assumed to be known. But clearly, calculating this as a vector times a matrix times a vector, and then also calculating the norm of the vector, this gives typically, if the matrix A is a matrix which is an n times n matrix, this is going to give us something like n cubed floating point operations for the denominator, and n squared floating point operations for the numerator. And clearly this is quite expensive numerically if the matrix is pretty large. However, this is a very simple way by which we can actually obtain a specific value for the learning rate. So remember now that what we typically do is that we replace this one with a parameter. So now I'm not putting a subscript k on it because I want this to be a constant, but it doesn't need to be a constant. But this is actually what we normally end up doing. And to calculate this quantity here, this one is numerically expensive. And that's why we actually end up calculating a gradient multiplied with a learning rate, where we find it cheaper to actually make the simulations with different values of the learning rate. So what we are going to see now are different implementations of what we have here. But before we move on, let's now look at some of the problems which we may face when we're actually looking at these simpler methods here. So let's take a simple example. And let us assume that we have a function of x1 and x2, and we can actually rewrite this in terms of a vector times a matrix, etc. So this is going to be f, and it's a function of a vector with x1 and x2. So I can actually rewrite this one in terms of a vector, which is now given by x1, x2. So this is the transposed. And then I'm just setting up a matrix, which is given by 2, 1, and 20 here. And then it's multiplied with a vector x1, x2. And then I have minus. And this is, sorry, this should be a minus. And minus. And then I have a vector which is given by 5 and 3 multiplied with x1 and x2 here. If I multiply this out, this is the same as x1 squared plus x1 times x2 plus 10 times x2 squared minus 5x1 minus 3x2. It's easy to calculate the gradient. So I can set up the gradient either in terms of the components, d of x1, x2 with respect to x1. And when I take the derivatives, this is simply 2x1, and then it's given by plus 2 minus 5. And then I can do the same here of dx1, x2, of dx2 here. And that is given by x1 plus 20 times x2 minus 3. Or you can rewrite this in terms of the vectors, because we know that d of f of x is going to be given by a times x minus b, and where we actually have defined f of x is equal to 1/2 x transpose times a times x minus x transpose times b. And if you go back to the expression which we have, this is actually the explicit case which we've been looking at, where we have two variables, x1 and x2, and this gives us obviously a second order polynomial in x1 and x2. So when you now calculate the derivatives here, what you want to do now is to solve this iteratively. So that means that we have the following expression. And let's just look at some terms. This is actually a very useful example in order to gain some insight about what these gradient methods are doing. In this particular case, we can actually calculate this ratio here and find this parameter alpha k, which you have here. So you don't need to actually calculate this gamma with different values here. But let's take a look at the iterative scheme, which we're going to set up. So the most brute force way is actually to use the standard gradient descent, not this steepest descent. So we would have xi is xi minus gamma of I, and then we have the derivative of the gradient with respect to x. And now this is calculated for x of I here, where this is one of the values. This is actually given in terms of a vector, and that contains x1 and x2. So for a suitable step size, what we have then is that if I start with an x0, so I would typically have x0, f of x0 is larger than the next one, x1 is larger than the next one, etc., till we have reached to a local minimum, till it converges or till it reaches a local minimum. So let's just plug in a value here. So the value which I plugged in now is just a value I chose randomly, 0.085. And then when I start the first iteration, so if I do x1, I also have a guess for x1 or x0. So we start with a guess for x0, and we simply put that one to -3 and 1. And then what we find then is that x1 is equal to x0 minus gamma 0 multiplied with the gradient of f calculated at x0. So then we just have to go back to the expressions which we have here for the gradients, and we simply plug in the values of -3 for x1 and 1 for x2, and then we are going to get a new x1, which becomes equal to -1.98, and then we have 1.21. So we are moving in the same direction for x1 and x2. So we move from -3 to a smaller value, -198 for x1, but we move to a larger value for x2 from 1 to 1.21. Now, the next value, x2 here, is then going to be equal to -1.32, and then I have a -0.42. Now, if you make a plot of this function, you will have something which looks like this. So let's try to make a plot of this specific function. So and I invite you to actually write a small code which tests the convergence with a given learning rate for this specific problem here. This is a pretty simple problem. And the thing which is simple with this problem is that you can play around with it for different learning rates, but you could also try to implement the steepest descent. So one of the things which we're going to see is that there are ways by which we can speed up the standard gradient descent. Then we are going to use this way to speed up the gradient descent when we move over to a next method, which is called stochastic gradient descent, which is normally the method of choice when we have lots of data. And I will come back to why the stochastic gradient descent is the preferred method compared with the standard gradient descent or steepest descent. So if I make a plot of x1 from, let's say, -4, we have a 0 here, we have a 4 here, and I take x2, I've actually picked out the minimum because it's pretty easy to find the minimum here. If you go back to the algebraic expressions you have for the derivatives with respect to x1 and x2, it's easy to see where this one is actually to 0, because what you're doing now is you're simply requiring these equations to be 0. So you have two equations with two unknowns, and that means that you can actually find the answer for x1 and x2. So with that, when you make the plot, so let me just plot here, what you will find then when you're setting in different values of x1 and x2, and remember, so this is a projection into the plane of x1 and x2 of the function. You will see then that there is a minimum around some values here, and then depending on the values, you're going to get this kind of contour circles, and so on. So when you take the first vector, you started with -3 and 1, so that means minus, so sorry, this was -3, let me just, -3 and 1, so that means that we started somewhere here. This is where we had the starting point, and then we did the first iteration, and then we got something like this, and then we go down again, and then when you continue, so this will be your x1, this will be the x0, x2, and then when you continue, then you will get something which goes like this, and it could also be something which converges very, very slowly to the desired minimum point. So the question then is whether we can actually increase this convergence. So one of the typical problems which we face is actually that the convergence of these gradient methods can be slow if the curvature of the optimization surface, which is the surface you see here, is, if this curvature of the optimization surface is such that there are regions which could be what we normally call poorly scaled, and so the curvature is such that the gradient descent steps jumps between various kind of walls and approaches that minimum in very, very small steps. And this is something you can verify if you encode the expressions for this specific example, choose this learning rate, and then you plot the different convergence steps. We are going to see another example in just one dimension, just in some few moments here. So there are ways to actually improve this type of convergence without going back to the steepest descent or more advanced method like conjugate gradient, where you actually have to evaluate. If you now scroll back here a little bit, so when we are dealing with methods like the steepest descent or the conjugate gradient method or more advanced methods for gradient descent, what we always end up with is to have to evaluate matrices of this type. Alternatively, the brute force way would be to actually evaluate the inverse of the Hessian matrix. Now, this recipe gives you an adaptive step size because now we recognize this alpha k as our step size. And you can see if you look at this expression here, the only thing we've done is to replace alpha k with gamma. So the question around which all of these optimization schemes rotate is, can we calculate the gradients more efficiently? And two, can we have a scheme for updating the learning rate without having to calculate matrix quantities like these? This is, if you want to look at this in a kind of overarching way, this is actually what we are worried with here. And what I'm going to show you now are some of the standard methods which actually use to update this learning rate without having to calculate this expensive quantity here, or even more expensive to have to invert the Hessian matrix. So any questions so far? So feel free to use the chat here since we are not having an in-person lecture today, because I hope you see the overarching theme. So these kind of methods which we are dealing with, so let me just write it down again. So there are essentially two overarching themes. One, the first theme is actually an efficient calculation of the gradient, and that's going to lead to the stochastic gradient descent, efficient calculation of g of x. And two, ways to update the learning rate without having to calculate, let's say, the inverse of the Hessian matrix, ways to update the learning rate. Gamma without computing, for example, the inverse of the Hessian matrix of H, or as we saw in the case, or for steepest descent, which is one of the other methods we could be tempted to use, that would be to calculate this parameter gamma of k, which is now given by the gradient transpose times the gradient, and now this is the gradient multiplied with the Hessian matrix multiplied with G. So this is what you would have to calculate if you were to use the standard steepest descent method, which is actually one of this, the simplest possible methods which we can deal with. Now, one of the ways to circumvent this is something which is called gradient descent with momentum. With momentum. Or what we could say, which is actually a better word, but it was inspired by the solution of Newton's equation, where you had a term which is velocity proportional, which introduces a kind of friction term, and we're going to see how this method arose. But the gradient descent with momentum or memory is actually better. So what we are going to do now is that the new gradient descent step, which gives us a new parameter beta plus 1, is going to be proportional, or it's going to have some memory from a step before the previous step. But let's now look at the motivation for that. And this is a simple way by which we can actually improve the convergence of the standard gradient descent. This method is actually used in stochastic gradient descent as well. And these are efficient ways by which we can circumvent some of the slowness in the standard gradient descent, which also translates into the slowness of the steepest descent also. So let's look at the motivation. So this starts with Newton's equation of motion, which I assume that many of you are pretty familiar with, of motion for a particle, which now is under the influence of a drag force, or you can think of a friction term, which is velocity dependent, and an external force. So Newton's equation of motion with external force and a so-called drag or friction term. And this drag and friction term, they are velocity dependent. So this is a kind of analogy which we can make in order to understand how we can now try to update this learning rate or the gradient descent step by a very simple trick which introduces a memory about previous steps. So let's take a quick look at the Newton equation. So we know that the force F of x is actually the derivative, it's actually the gradient of a potential. So this is where our gradient comes back. So this is the gradient of a given potential here. And the equation which you have, the famous equation with the acceleration, so this is dx of dt plus, and then we have a drag term or friction term. So if you are sliding an object along a plane, there would be some friction, and we assume that this friction is velocity dependent, and then there's a constant which depends on the physical parameters, and this is given by minus this the gradient of the potential, which gives the force. So this is actually our force, F of x. But I'm going to keep the gradient because this is going to give us the kind of gradient link with the gradients. Now, what we're going to do after the break is actually to discretize the equations, but let me just discretize it immediately. So I'm going to have a dx, the second derivative. When we take the most standard formula, this is x of t plus delta t, one time step, minus 2x calculated at t, plus x, this is a famous formula for the approximation of the second derivative, divided by delta t squared. Then the next term which we need, and here we just take Euler's forward method. So this approximated with x of t plus delta t minus x of t divided by delta t. So after the break, we are going to plug this into the equation for Newton's law with the external force and the drag term. And then we are going to see that by some simple recognitions, we are going to see that we can translate this in terms of the learning rate, the gradients, and a term which represents the memory. And this is the analogy and the origin of the name momentum-based gradient descent. But let's wait till after the break. So I will suggest now that we take a small break and we meet back at 1/4 the hour. I'm going to put the recording on pause during the break. So before the break, we were trying to make an analogy with a way to improve the gradient descent method by updating the learning rate in a specific way. And this leads to the so-called momentum-based gradient descent. And the analogy comes from the solution of Newton's equation, where we have an additional friction term. And remember now that when you look at the friction term, like this term here, so it will be this term, this is actually the velocity times a parameter. And that plays in a certain role, the role of a momentum here. This is proportional to the momentum, because you know that the momentum is given by the velocity times the mass, and dx dt is actually the velocity. So the kind of analogy which we are going to make now is in the rewriting of the equation, where we now discretize the second derivative and the first derivative using two of these well-known formula. Now, when we do that, the next step, which we can do now, is to define two quantities. So we are going to rewrite the equation. So I'm going to define a quantity which I call for delta x of t plus delta t, which is simply the difference between x at the time t plus delta t, and later you will see that we are going to replace this with the iterations, and now x of t. And then we have a delta x of t, which obviously has to be x of t minus x of t minus delta t. And this is going to give rise to this memory term, which we mentioned, where we now have an input from the iteration before the one we started to look at. Now we can now rewrite the equation, because you see we have a term here which has an x plus delta t, a term here which is an x plus delta t. We are going to multiply away delta t squared, and we are going to then get a term which goes like delta t in front of here, delta t squared here. We will have a delta t squared here. We are going to have a term m plus mu times delta t multiplied with this one. So when we now just collect the terms and rewrite everything in terms of this delta x of t plus delta t and delta x of t, what we are going to get then is a term x of t plus delta t is equal to minus, and then we have a delta t squared divided by m plus this term mu of delta t, and then we have the derivative of the potential, which we are going to replace with a gradient later, plus m divided by m plus mu of delta t times delta x of t. So this is just a reshuffling of the equations which we had. And then we are going to define new constants. So I define a parameter delta, which is simply the last term in front of delta x of t. So that's an m plus mu of delta t. And then I'm going to put in a new parameter, which I am going to recognize as the learning rate. And so I'm using the same symbol gamma, and I'm going to have a delta t squared divided by m plus mu of delta t. So that means now that what I have is that my delta x of t plus delta t, which is a difference between the new and the previous iteration, is given by minus gamma, and then I have the gradient of the potential with respect to x plus delta times delta x of t. Now this delta is going to play the role of a memory term because this has knowledge of the parameters of the iteration x of t and the step before x of t minus 1. So this plays the role of a memory parameter. Notice also that if you look at this term delta, which is given by delta t, which we have here, m divided by m plus mu times delta t, when you now let mu become infinitely large, what you're seeing then is that this term in the limit, when mu is large, and mu is a positive quantity, keep that in mind, then delta t is getting closer to m divided by mu of delta t here. So that means that the memory, this memory term, is going to scale in a specific way in the limit of large values of this parameter mu. So you can also see from this expression here that delta takes values between 0 and 1. So if mu goes to infinity, then clearly we have 0. If mu is 0, then we have just 1. So delta takes a values between 0 and 1 here. Now, if you now want to bring back your parameters beta, what we're going to do now is to let this x of t, with t is time, is going to be replaced by beta of I. That means that x of t plus delta t is going to be replaced by beta of I plus 1. So delta t is now one specific time step, whereas in our case, this is one specific iteration. I'm going to replace delta x of v of x. That's going to be replaced by g, the gradient which we have, as a function of beta of I, the iteration I. And then what we see now is that this delta of beta of I plus 1 is going to be simply equal to beta of I plus 1 minus beta of I. And my delta beta of I is going to be equal to beta of I minus beta of I minus 1. And if I bring everything back, then I have a new updating scheme, which is a beta of I plus 1 equal to a beta of I, as before, minus a gamma. And now I'm going to put a gamma of I here, because later we are going to look at ways by which we can scale this gamma of I. And then I have a g. Actually, we have not the g, but we have a parameter g here, which is our gradient, g of beta of I. But then I have a plus a delta of beta of I minus beta of I minus 1. So what I'm doing now in the iterative step, I'm bringing in some kind of memory about the previous steps. And what you will see then is that this momentum gradient descent, as it's normally called, or memory gradient descent, that helps the gradient method to gain speed in directions with persistent but small gradients. So you will see now when you compare the momentum gradient descent with the standard gradient descent that you can actually get a speed up of the iterative process towards the optimal values for the betas. Now, this is normally rewritten in the following way. You will often see that in the literature, often rewritten as a term which is called V of I, which is given by this delta of beta of I minus beta of I minus 1. And then we would have our parameters beta of I plus 1 equal, and this has also the gradient, minus gamma of I multiplied with g of beta of I. And this is often then rewritten in terms of this parameter v of I. So this is the way you would calculate it. And if you want to improve your algorithm now by including the momentum-based gradient descent, so the algorithm would then require, and you have an additional hyperparameter, it requires a learning rate as a parameter. So this is something you have to feed in. And later we're going to see how you can actually improve upon the learning rate by having a kind of scheduler which allows you to optimize the learning rate as you move on with different iterations. And there are many ways of doing this. There is nothing which is set in stone here. This is a kind of practitioner's approach where you try different scalings of the learning rate. But you require learning rates in order to start the algorithm. What you also require, you require the so-called memory or momentum parameter. So in some textbooks, you will find it as a memory parameter, in other textbooks as a momentum parameter. So you require the momentum parameter. And these become hyperparameters in your machine learning, in your given machine learning algorithm. And this quantity is proportional or has a range between 0 and 1. So you have to choose a value here between 0 and 1. And you will need to play around with it in order to find the optimal way. And then you initialize. The parameter beta. So you would typically set a parameter beta 0. And this parameter v. And so that means that you would actually set up a v0, which in this case, but you have to be a little bit careful because you don't have v of minus 1. So it means that you would actually start with a b1, which has some specific value for v0, which leads to a specific value for v0. So the algorithm then goes like, while stopping criterion not met, which could be the convergence criterion you have, stopping criterion not met. Then you compute the gradient. So I'm just setting up the algorithm in words. Compute gradient. The next step, when you compute the gradient, then you compute the velocity update, or the v, compute v. And then when you have v, then you apply the update, apply v of I to the update, beta of I plus 1 is equal to beta of I plus this term v of I. And this is the end while. So it's pretty easy to implement. Now let's, unless you have any questions here, so this is the standard momentum gradient-based descent. Now there are other ways of implementing the momentum-based gradient descent, and one of them is called the Nestorov momentum-based gradient descent. And we are going to discuss that a little bit more tomorrow. But this is one of the simplest ways you can improve the standard gradient descent. And you can actually show mathematically that it helps the standard gradient method to gain speed in direction with persistent but small gradients. So let's take a look at a small run here, or small example. And one of the things I would like to invite you to is to take that matrix example which I had before the break, that simple function f of x, which is a function of x1 and x2, where you have simple expressions for the gradients and simple expressions for the function f of x, and try to optimize that one, and try to do that with and without the momentum-based gradient descent. Now, if you scroll down through the slides for this week, you're going to come down to, so I actually included many of the things which we went through last week, but there is when you now have gone through all this material here, and looked at the examples which we went through last week. So I just brought them up here just for the sake of completeness. But there is a simple example here on the gradient descent with momentum. So I have a function which you can see here, which is simply x squared. And clearly the derivative is x, 2 times x. And this is a standard gradient descent. So I have a bound for the solutions which I put up from -1 to +1. And then it simply evaluates the gradient. In my case, I actually have the explicit equation for the derivative. And then I simply set a step size. And then I calculate the gradient descent here. I put my bounds between -1 and 1. I set up iterations to 30, and then I have a step size of 0.1, and then I send over the function I want to calculate, the derivative with the bounds and the number of iterations, and then it plots the results here. So if I run this code, this is the standard gradient descent, and I invite you actually as a small exercise, you can take this example or just modifications of it and try the example which we discussed before the break of the function f of x1 and x2. So what you would see here is that this is a function of number of iterations, and we actually want this to have a 0 at f of 0 here. And in this specific, because we know that the minimum is at the x equal to 0, and we see that we are slowly approaching that. So we need something like almost 30 iterations before we actually reach the minimum. And here you can see the way we proceed, starting with a specific value, where we now started with a guess of 0.75. And here we calculate the function values, and we know that the optimal value is at 0. And the result here, you can see now that there is a pretty slow convergence. Now, you can replace this by your own momentum-based algorithm. So this is the same problem, but with momentum gradient. You see again the same function, the same derivative. And here I have a gradient descent, but where I now calculate things in terms of this momentum. And then I keep the change, the update from the previous case. And then I keep running. And you will see then when I run the code here that I actually need much fewer steps. You can see now after 13 iterations, I've actually reached a function value which with 5 leading digits is actually equal to 0. And you can see that when you plot the different values here, the gradients, you see you're getting much faster down to the ideal value here. So there is a question here that you can't find. Let me just take this question from the chat here. So if you look at the there should be, if you now go to so let's just go to the there should be a function. If you go to the website of the course and doc, and you look at the pub folder, and you go to week 39, I'm actually running this one from here. Oops, maybe I may have not updated my files here. That's a good point. So let me try to fix that as soon as possible. So while we, before we move on, let me see if I can fix this one as soon as possible here. So let me just do that so that everybody has access to the file, because I'm just running this from my laptop here. So let me just try to do that. So it should have been there because I should have uploaded this to the GitHub address. So let me just see here. So it may take some time before it's up online here. And if it still persists, I'm going to try to see what happens here. Okay, so it may take some time before it gets uploaded to the website. So it should. Okay. Let me just do one more thing here. So let's see now if it's back again. Let me just check that it actually came there. There it is. So that should be resolved now. I don't know why it didn't upload the file properly, but now it should be there. So if you, there was a question in the chat about the missing Jupyter Notebook file here. So it should be there now. And if you can check it and see if it is there, then we can just move on a little bit. So what you see now is that with this momentum-based method, you're actually reaching the ideal value with fewer steps. This is a trick which is often used in many of these kind of iterative methods, that you actually keep some kind of memory about the previous stage. Now, in our case, what we are going to move into now is the calculation of the gradient, but not using all the entries in the gradient. And this is going to lead us to what's called the stochastic gradient descent. So keep in mind that what we have done now is simply to look at ways by which we could speed up the standard gradient descent without doing anything particular with the learning rate, but just keeping a kind of memory of previous iterative contributions. Now, we are going to look at how we can perform these calculations without calculating the whole gradient. So in the calculations which you saw here, we have in this specific case, we have the exact gradient, but in the examples which we discussed last week, one of the things which we did, if you now look back at the equations, is that we run through all the matrix elements of the gradient. So we have a matrix X of t, which has dimensionality number of entries n times number of features p. So we perform a matrix multiplication. We multiply that with a parameter beta. So a matrix multiplication, if this is a square matrix of dimensionality n times n, then we end up with n cubed floating point operations. So if you have a matrix of dimensionality 10,000 times 10,000, that means that in every iteration here, you're actually doing 10,000 cubed floating point operations. And this is clearly something you would like to reduce. And this is where this stochastic gradient descent comes in. And this is what we're going to spend some time on now. So that's simply a way to calculate the gradient in an approximative way without having to run through all the matrix elements and all the vector elements. So that means that we should not expect to get the same result as we did when we calculated this with the exact gradient. So any questions so far? So keep in mind also some of these things which we discussed last week. So the gradients are computationally expensive to calculate for large data sets. So in many cases in statistics and machine learning, the cost-loss risk function is a sum of terms with one term for each data point. And it's also, as we have seen, it's sensitive to the choice of learning rates. We compensated partly this by looking at the kind of memory parameter. But then when we have this kind of learning rate, one of the problems we face there is that all directions in parameter space are treated uniformly. So can we improve upon this? So there are two main issues. One, the reduction of the calculational complexity, which is addressed by stochastic gradient descent, and then tuning the learning rate so that we could actually get things learning rates, which may be different in different spatial directions, and also that the learning rate gets a kind of adaptive rule so that it changes values as we move on in the iterative process, without us having to evaluate complicated matrices which have to be inverted. So I hope you see this kind of a bigger picture here, which we are going to dive into now when we look at stochastic gradient descent. So if we scroll down a little bit, there is some general motivation which comes up first on the stochastic gradient descent, and then we're going to look at code examples. So stochastic gradient descent will also use methods like the momentum gradient descent. So the kind of machinery which we put up now is something which we will also implement when we are dealing with the stochastic gradient descent. So what we did now with the momentum-based gradient descent is not something which is limited to a specific way of doing the gradient descent, whether it's stochastic or non-stochastic. So let's now take a look at the stochastic gradient descent, and let me see if I can motivate for why we should use the stochastic gradient descent. There is a very nice video on the StatQuest link, what is stochastic gradient descent. Take a look at that one. So as he said, in gradient descent, we compute the cost function and its gradient for all data points we have. So in large-scale applications like this huge image database, which has millions of examples, then the training data is so big that it seems almost wasteful to compute the full cost function over the entire training set in order to perform only a single parameter update. So a very common approach to addressing this challenge is actually to compute the gradient over batches of the training data. This is also relevant if you want to avoid being stuck in a local minimum, because you could think of you placing yourself randomly in parameter space, and perhaps some of the directions you choose will actually not lead to you being stuck in a global minimum instead of a local minimum instead of a global minimum. So a typical batch, as we call it, so we compute the gradient over batches of the training data. So that means we may not include the full training data. A typical batch could contain some thousand examples from an entire training set of several millions. And the thing is that when you do this in smaller chunks, is that the matrix multiplication, which we need to do in linear regression, and also in other methods, when we do logistic regression, we also need a matrix multiplication. The benefit then is that the dimensionalities and the number of floating point operations then are actually smaller. So this batch is then often used to perform a parameter update. So in stochastic gradient descent, where we have only one batch, that means that we have the whole data set. And then we're just back to what we did before. So there is some confusion in the literature, because when you have only one batch, that means the whole data set. This is by people called stochastic gradient descent, or also online gradient descent. The only thing you do now is that you reshuffle your data randomly, and then you place yourself randomly and pick one of the points, and then you start computing the gradients. So this is actually less common, and this is mainly because in practice, due to vectorized code optimization, you can compute in a much more efficient way the gradient for, let's say, 100 examples than the gradient for one example 100 times. And you can easily see that when you look at the number of floating point operations you would have. So technically, many people refer to stochastic gradient descent as just a single example at a time to evaluate the gradient. But you will normally hear people referring to stochastic gradient descent when you have split the whole data in so-called smaller batches of data. So instead of saying mini batch gradient descent, people simply just say stochastic gradient descent. So sometimes you have to be a little bit careful with the wordings and see from the code what is actually meant. So strictly speaking, many people tend to use stochastic gradient descent or should use stochastic gradient descent as just you doing a stochastic approach to it by taking the whole data set. But in general, what you do then is that you split everything in mini batches, and sometimes you choose values which are modules of 2 and powers of 2 here, because many vector authorized operations actually work faster when the inputs are sized in powers of 2. So when I say stochastic gradient descent now, I'm going to mean stochastic gradient descent with mini batches. And from the examples, you will see now how we can actually run these cases and analyze our results. So stochastic gradient descent, if you think of what we have done previously, we run over the whole data and we calculated the gradient of every C of I here. So that means that what we did in the examples which we discussed last week was simply to calculate all the contribution to the gradient. So this randomness is actually introduced by only taking the gradient on a subset of the data, and these are called mini batches. So if you have n data points and the size of each mini batch is m, then there will typically be n divided by m mini batches. And these batches are normally in the notes here, they're just denoted by b of k. So the example which you see here is pretty simple. So if you have something like 10 data points and you choose 5 mini batches, what you would have then would be batch 1, which could be x1, x2, and then up to batch 5, x9 and x10, or they could be sorted randomly. So if you choose m equal to 1, you have only one single batch with all the data points. If you choose m equal the number of points, then it results in a mini batch for each data point. So the idea is that you actually approximate the gradient by replacing it with a sum over all the data points with a sum over the data points in one of the mini batches picked at random in each gradient descent step. And from the codes, you will actually see what is being done here. So typically what you do then, you have a gradient descent step, which now looks like this. So you update your parameter beta, and you sum over the batches which you have, and you compute the gradients. Where this k, which you see here, this k here, is picked at random with equal probability from the number of batches you have. And an iteration of the number of mini batches is commonly referred to as an epoch. So when you run through all the mini batches, you have one epoch. So that becomes a parameter. So the number of batches becomes a parameter, and the number of epochs becomes a parameter. The learning rate is a parameter. If you are using a regularization term, you have another parameter like you had in Ridge and Lasso. And then in addition here, you you will also have the way you tune your learning rate. That will also introduce a set of parameters. And there are many ways by which you can tune the learning rate. So the typical example code which you could have, you specify the number of data points, you specify the size of each mini batch, and then you find the number of mini batches. And then you also define the number of epochs. That's the time you run everything, the number of times you do that. So here you would have number of epochs, and you run over all of them. And for each case, you run over all the number of mini batches. And then within each mini batch, you pick the kth mini batch at random, compute the gradient using the data in mini batch b of k, and then you compute new suggestion for the parameters. And then you keep updating. So the question is, when do you stop? And here, there is no unique recipe. And that's one of the big issues when you're dealing with machine learning, is that you have no additional parameters, the number of epochs, the number of times you rerun and recalculate the gradient. But you have also the number of batches, which becomes a parameter. And then the question is, how do you actually change, or if you want to change, the step length? So there are many such schedulings of the learning rate, and we're going to see some of them tomorrow. But in the meantime, I just invite you to take a look at some of these articles here, actually, how to set up learning rate schedules and adaptive learning rate methods for deep learning. So this is an active research field, and in many cases, you cannot a priori say whether this learning rate schedule functions better than another one. And this becomes a new set of parameters or functionalities which you will have to test when you are running your machine learning algorithms. And in project number 2, this is one of the things which we are going to play a little bit around with. What is the best scheduler for timing or for making changes to the learning rate? So one approach is given here. So it's a kind of decay rate. Tomorrow we're going to list the different ways you can do this. But you could now think of letting this parameter E run from 0, 1, 2, 3, where that denotes the current epoch. And then you fix two parameters, T0 and T1. And these are fixed numbers. So you would have to fix them before you start the calculations. So they become parameters. You can now let this T be something which varies with the number of epochs and the number of mini batches, plus I, which is a number of iterations here, or number of times you run through them. And then you would have a function which looks like this. And as I said, tomorrow we're going to look at other ways. I mean, the simplest possible way is actually to set the learning rate to be a constant, and then select values for the learning rate and simply run your machine learning algorithm with a fixed learning rate all the time and perform a stochastic gradient descent. So in this specific case, you will define this function like that. You can fix parameters. So often this T1 is chosen to be larger than T0. Here we choose a number of epochs, 500. This becomes another parameter one has to tune, and the same with the number of batches or mini batches. And then it would simply run over here. But now we're going to look at a code which has a number of mini batches which varies. So this is going to be our first examples where we now pick up the same cases we looked at last week. So I'm making some kind of vanilla data here, and I'm setting up X in terms of a random number according to the uniform distribution. And then I have a data set which now contains also random noise here. And in the beginning, I'm going to run this without the random noise in here. Then I'm setting up my design matrix. I want to fit a first order polynomial. And as you see here, I have the standard inversion machinery where I keep the intercept. And then I print now the values of theta. I calculate also the second derivative of my cost function. This is just plain standard linear regression, ordinary least squares. And I calculate the eigenvalues in order to find out which value of the learning rate I should choose. And in this case, I take the maximum eigenvalue. And this is within the parameters for lambda, which will give me a converged result. I haven't put in a stopping criterion, so I just do 1,000 iterations, pretty brute force, not very intelligent. And then what we have then is my standard gradient descent, where I now run over all my data. And this is seen here, so there is no approximation made here. And then I print the theta or the beta values from my own approach. And then I make a prediction just to see that I get the same as I would get with also the standard if I were to call, let's say, scikit-learn. But in general, we know that this functions correctly. And now I'm setting up my stochastic gradient descent because I don't want to calculate or loop over all the data points in the calculations of the gradient. This is still a very small case. Then I define the number of batches. I define the number of epochs. I define this parameter T0 and T1. Tomorrow we're going to look at other parameters. I give a random guess to my unknown parameters. So I have two of them. I just give them values according to the normal distribution. And now what I'm doing here is that I'm setting up a loop over the number of epochs. So this is a number of times I'm going to repeat the calculations. I'm going to run over the whole range of batches. And now I fix a random index, which now sets up the data points which I'm going to use. I find the value of x of I and y of I in this small region. So this is actually my random index starts here and it goes to random index plus m. So keep in mind now that I picked up my random index randomly in my data set. And with that, I'm now finding out the x values and the y values. And here I calculate the gradient, but now we have to keep in mind that I need to divide it by the number of points which I have in a batch. So the size of the batch is 5. Remember now that when we did this with the standard linear regression and calculated the gradient, I divide by all the data points n here. But now I have to divide by the number of points which I have, or the number of data points in a specific batch. And in this case, this is 5. And then I update my learning rate. We can leave that constant, and I invite you to play around with it. And then I calculate my new updated for the parameters beta, and then I print them out, and I compare them with what I would get with the values from my optimal code. So you can see now that my own inversion is given if I just invert the matrix and use the analytical expressions. And then my own gradient descent, when I use the correct learning rate, gives me also a result which is exactly the same as I would get from matrix inversion. And you see now that the gradient descent here, since now I'm calculating approximately the gradient, this doesn't give me exactly 4 and 3. So you will get results which will differ from the exact ones. And clearly when you have a one-dimensional problem like this, with just a linear function, there is no way the stochastic gradient descent can beat the standard gradient descent. However, the benefit of this is when you go to larger data sets, I mean, the hope then is that this averaging with the stochastic gradient descent is something which allows you to actually calculate this without much problems. But you can see the quality here. Now, there is a specific thing to think about. There are lots of technicalities when we do this. And in this code, we have used replacement in setting up the mini batches. And if you go to the link which you see here, and I actually invite you to take a look at this link till tomorrow, there is a discussion on whether you should do that or not. And this is an unsettled debate. And I invite you to take a look at the link by Sebastian Rashka, which has an excellent list of material and machine learning methods. He has actually written an excellent textbook, by the way. So before the break, we actually went through the momentum-based methods, and the topic which we are going to look at tomorrow, in addition to the momentum-based method, are adaptive gradient methods, which means that we are now going to find a way to adaptively change the learning rate. And tomorrow we are going to meet methods like AdaGrad, root mean square propagation or RMS prop, and ADAM. And after that, we are going to look at more examples, and we're also going to look at how we can calculate the gradients without setting up an analytical expression, but calculating the gradients with automatic differentiation. So these are technicalities which you will find very useful. And methods like AdaGrad, root mean square propagation, and ADAM are widely used in machine learning optimizations. So we are going to have ways to update the learning rate, and that introduces additional parameters. When we do the stochastic gradient descent, we split everything into epochs, and then for every epoch, we run over a certain number of batches. That introduces 2 more parameters. So in addition to the learning rate, we have 2 more parameters, the number of epochs and the number of batches. And clearly, if we are doing a regularization term, in the method, if you're plugging that in, we will also have another parameter which we need to fine tune. So you will see now that as we move on, the number of parameters is just going to grow. And you could think of these different ways to adapt the learning rate as another type of parameter tuning. And they can give different results. And some of them work well for convex functions. Some of them work better for non-convex functions. So like AdaGrad is really tailored to problems where you have a well-defined convex function. RMS-prop and Adam can be used on, in principle, any type of function. And Adam seems to be the kind of preferred method. But these are things which we will discuss a little bit more in depth tomorrow. I hope you're seeing the wood for the trees with all these kind of parameters. So just to summarize, the overarching thing is, one, we want to avoid to compute the full gradient to run over all the data points, because when we are getting into neural networks and data-rich environments, this is going to be extremely expensive unless we can invert the matrices and find nice analytical expressions as in ridge and ordinary least squares. But in most cases, we will have to calculate gradients numerically. Two, the adapting of the learning rate to the specific problem we have. We've looked at the momentum method, which does not exactly deal with the learning rate, but it's a way to speed up the standard gradient descent and stochastic gradient descent. But tomorrow we need to look a little bit deeper into ways which we can tune the learning rate. And that is going to lead to these methods, which are called AdaGrad, root mean square propagation, Adam, and many, many others ones. So this is a very open research field, and there's a lot of interesting mathematics to try to understand. In many cases, you just end up with ad hoc recipes, and if they work, they work. And then people just stay with the methods which work best for their applications. Okay, so we're going to stop here, and then we meet together again tomorrow, but then we will be in the standard lecture hall. So I'm going to stop the recording.